open ocean stretches as far as the eye can see. Quiet and calm, almost tranquilizing. Looks peaceful, right? But it's anything but. Beneath this seemingly calm surface, there is a constant battle for survival, where the rules of life and death are governed by multiple interactions among many different predators and their prey. To avoid being caught, small fish aggregate into larger groups, creating a confusing, shimmering mass that makes it challenging for the predators to single out an individual target. Safety in numbers, that's how you can call it. However, then you might ask yourself, if prey uses a collective as a defense strategy to increase their odds of survival, why wouldn't predators aggregate together as well to use the power of the collective to increase their hunting success? To figure this out, let's get on board of the boat and go far offshore to find the predator aggregations. But how do we spot them in these vast waters? Look for birds. Bird flocks are the perfect indicators of the locations where the predators have pushed fish schools to the surface. Have you also spotted that tiny dorsal fin above the water? I know what you think. It's a shark. But no, in truth, sharks in the wild very, very rarely swim with their dorsal fins above the surface. Then who is it? Let's put our heads into the water. And we see Marlin, and another one, and many more around them. 2 meters long, with blue stripes on the sides of the body, a dorsal fin resembling a sail, and a sharp bill to slash their prey. These impressive predators can be found in tropical waters, offshore Baja California, Mexico, hunting together not far from the surface. If we are lucky with the weather, using drones, we can get a bird's eye view perspective on the whole hunting process. Here you can see a snippet of the footage from the last year's field season, about 30 marlins striking at a sardine school. Being pushed up to the surface from the deep blue, sardines are chased for long distances, with alternating stationary phases, where they are blocked by multiple surrounding predators around and below, such that there is no direction left to escape. How do predators coordinate their movements and attacks to do this and achieve the success? What are the mechanisms behind these complex interactions between two collectives, a collective of predators and a collective of prey? To answer these questions, we develop computer simulations where we can take control over the interactions and test our hypothesis. Here you can see such an example of a simulated hunt. Looks similar to the real one, right? So let's have a closer look. Here, on the left-hand side, you can see what happens without interactions between predators. So the predators are indicated by the dots in red color, and prey are dots in black. As you can see from the side, it might seem that the predators are actually interacting with each other, if they're creating some sort of groups chasing the same parts of the prey swarm, resulting in its high fragmentation and dispersion. However, without interactions, the predators also end up coming very close to each other, which is quite dangerous for them if you remember their long and sharp bills. And here, on the right-hand side, you can already see that by introducing such a simple interaction rule as keeping distance away from each other, the predator group is able to control and hold the prey in the confined region, performing at the same time attacks by the individual members in turns, so that they can exchange their spatial positions to come into the middle of the prey group, namely to perform an attack, as it's actually observed in the real biological system. At the same time, from the prey perspective, the prey might want to keep tightly together as it helps to prevent multiple attacks by many predators at the same time, since predators have to trade off both attacking the prey and keeping distance away from each other, resulting only at one predator attacking at a time. But what is prey actually doing when it's finally attacked by a predator? If we zoom in on the footage, we can see that as soon as the predator is approaching, the prey group splits into two subgroups, fleeing away by either sides of the predator and coming back nicely together behind its tail, facing the same direction of motion as at the predator at the start of an attack. Such a phenomenon is widely described in biology as fountain effect. Functionally, it allows prey to get into a safe spot behind the predator, despite its much slower speeds but greater maneuverability. To model this, we have to define how a predator and a prey collective interact with each other. To give you an idea of such a potential underlying mechanism, imagine that there is someone behind your back, potentially chasing you, much faster and bigger than you. You might want to keep an eye on what's happening behind and go as far as you can at the same time. If your neck is not agile, you have to reorient yourself such that you can see the threat. Since you and your stalker are continuously moving, you have to reorient yourself at each step, eventually ending up moving like this, such that your trajectory naturally results in an arc. Also, don't forget that you are not alone and you are part of the fish school, such that your response will infect the entire group, such that those who cannot see the threat yet will respond rather sooner than later, and hence will be able to escape, just because of you. We have found out that such a simple mechanism on an individual level produces not only these beautiful patterns on the collective level, but also allows to maximize the distance from the threat for each individual member in the group, and at the same time to minimize the time needed for the whole collective to recover after an attack and to prepare for the next one, resolving the existing trade-offs. Surprisingly, we have found out that this is the best strategy, even if there is no blind spot behind me, even if I can see behind my back. By controlling the predator position in the simulation, we were able to predict the beneficial sites of attacks for the hunters and for those being hunted. Combined together with empirical data, there is an evidence that both types of attacks are equally dominant, supporting our predictions and indicating that there is ongoing arm race, where the predators are attempting to attack the groups in the ways facilitating their hunting success, and the prey are attempting to flee in ways maximizing their survival chances. Using computer vision technology, we are now able to get the fine-scale trajectories of the predators and extract more data to inform our models better, to broaden our understanding of the collective intelligence. But how can we now transform our models into artificial agents, like robots? Before Pavel will explain that to us, don't forget to visit our exhibit, Interacting with the Fish School, where the presented simulation of the prey school is projected onto the floor and can react to human motion in real time, like the real school of sardines to the Marlin attacks. Try to split the fish school yourself and see whether you can trigger the fountain response the same way as the Marlins do. Or you can try to do it with the help of a little robot, Frank, so you can give him directions where to go, or he can do it completely autonomously, alone, without your help. But more about this from Pavel. Thank you very much.